Okay, today we're looking at section 7.7, which is exponential growth and decay. Hopefully by the end of this lesson you can say that I can model exponential growth and decay. So the two pictures here we have to the right, we should have seen in the last section where if you have an exponential function, you're either going to get one of these two graphs. You're either going to get one that increases or you're going to have one that decreases. If it's increasing, we oftentimes refer to it as an exponential growth, and if it's decreasing, we oftentimes refer to it as an exponential decay. So some notes that you definitely want to have down. You definitely want to have down this green box for your notes. So the C is going to be our initial amount, what we start with. The T is the time period. And then 1 plus R represents our growth factor, and the R is our growth rate. And again, if you see exponential growth, you're going to see it increasing from left to right if you're looking at a graph. Okay. So there would be our notes that you want to have. Pause the video if you need more time, but I'm going to move ahead. So what kind of things we're going to be doing? You might see something like this. So a wildlife manager determines that there is approximately 200 deer in a certain state park. The population is growing at a rate of 7% per year. How many deer will there be in the park after 4 years? So if we take a look here, back at this one, again, here's the type of equation we're going to write. Y equals C, parentheses, 1 plus R to the T power. So we're going to have Y equals C, parentheses, 1 plus R to the T power. So again, our C is our initial amount, and if we read the problem again, you'd easily see that the initial amount that we had was 200 deer. If we look closely at it again as well, we can see that the growth rate is 7%, so we'd have a 0.07 because that's 7% as a decimal. And the question becomes, first of all, this right here would be our growth model. Okay, it doesn't ask this question, but I just wanted to point that out to you, that that would be considered a growth model. If we wanted to solve the problem, we would put in a 1, or excuse me, a 4 for the time. So now, I have an extra 1 in here. I think I got that. So I have 1 plus 1.07 to the 4th power, or we could say 200 times 1.07 to the 4th power. So simply using a calculator, type in 1.07, raise that to the 4th power. The answer you get there times 200, and we would get approximately 262 deer. Okay? So that would be part A. Part B now asks the question, well, how do I know when there's going to be 350 deer? So the 350 now becomes the Y. So I'd have 350 is equal to 200 times 1.07 to the T power, because I don't know how much time. So now to solve this, we can simply divide by 200. So I take 350 divided by 200, and then get 1.75 is equal to 1.07 to the T power. So now, to figure that out, you can just do, make kind of a chart to figure out what T would be. So you put in 1.07, say, take it to the 5th power. Am I close to 1.75? Not quite. So I do it again, 1.075 to the 10th power. Okay, so I know it's somewhere between 5 and 10 because after 10 it would be 1.96. So I do a 1.07 to the 7th power, and not quite there, so 1.07 to the 8th power, and it's between 8 and 9 years. Okay. Next type of question you might see questions like this. So identify the initial amount and the growth factor. So the initial amount in the first one here would be 2. The growth factor would be a 3. Okay, if I look at this next one, the initial amount is 5, and the growth factor is 1.06. Okay. So now we're going to start looking at some decay problems. So if I look at the decay problem here, C is the initial amount again, R is your rate, and your decay factor is the 1 minus R, and T is again your time period. So what kinds of questions you might have here? Maybe something like this. Identify the initial amount and the decay factor. So the initial amount, again, here, if I could spell amount, maybe a little better. Amount would be 4. The decay factor would be 0.2. Okay, and then the second one, you should have a initial amount of 3, decay factor of 0.9. Okay, so if we look at a problem like this, now we're looking at another formula, and this is another formula that needs to be in your notes, talking about compound interest. Okay, so if we use this formula to do these two problems, so it asks find the balance in each account after the given period of time. So 800 or 8,000 principal earning 5% compounded annually for 6 years. So for this one, we simply start plugging in some things. So P represents our initial deposit. So in this case, we'd have $8,000 was our initial deposit. We'd have 1 plus R as our rate, and our rate was 0.05, and divided by the number of compounds per year. And if it's compounded annually, that means it's going to be done once every year, and this is going to be done for 6 years. So we would technically have a 1 times 6, but that's really just 6. So really what I have is 8,000 times 1.05 to the 6th power. So again, just use your calculator. 1.05 to the 6th power. The answer you get there times 8,000. And what we have would be 10,720.77 dollars. So $10,720.77. Okay, so if we look at this next one, so I got an A is equal to 500. This time 1 plus, again, our rate is 4%, so 0.04. This time it's compounded quarterly. So quarterly means 4 times a year, so I'd have a 4 down here. And then after 10 years, this again would be a 4 times a 10. So if I do this, what I'd have is 500, and if I do the math inside the parentheses, you'd have 1.01, and that would be to the 40th power. Okay, so what do I get here? I got 1.01 to the 40th power, and the answer you get there times 500. So after those 10 years, you'd have approximately $744.43. Okay, next question. Tell whether it's exponential growth, decay, or neither. Okay, so the first one, we've got a base that is larger than 1. So this would be a growth. Okay, if I look at the second one, our base is less than 1. So I know that this is a decay. Okay, if I look at the next one, our base is a variable. So this is not one or the other. So we'd say that this is neither. And the last one, we have a base that is less than 1. So this is a decay. Okay. If you have questions on those, you can ask me on those tomorrow. Let's keep on moving. So, this is very similar to a problem we've done before, so I'm going to pass over this one. Here's one that is a decay problem, so we're going to take a look at that one. And so, this would be a decay, so our y is equal to a c times 1 minus r to the t power. So my initial amount was 3,000, and then I'd have a 1 minus 0.15, and that would be raised to the fourth power. So I have 0.85 to the fourth power, which is 0.52. So I have 3,000 times 0.522, which ends up being approximately $1,566. Okay. And then the last one, just looking at a graph, can we tell if it's a growth or decay or neither? So hopefully we can look at the first one and say that's neither. Second one, we can say that that is a growth. Next one, we hopefully can say is a decay. And the last one, hopefully we can say is neither. Okay, that is all I have. Hopefully that makes sense to us all. And again, come with questions tomorrow if we're not quite sure. And that is a wrap.